All right, let's go ahead and get started here. What we're going to do is we're going to talk about titrations today. And so before we take the notes, I am going to go ahead and go over what a titration is and give you an example of one. And just a disclaimer, it is a very rough example of a titration. But what a titration is, it's where you have an unknown concentration of acid, let's say, or an unknown concentration of base. And what you do is you neutralize that acid or base with a known concentration of acid or base. And so because we know the concentration of what we're titrating it with, we can then calculate how concentrated the unknown solution is. And so I'm going to go ahead and sort of give you an example of this right now. But if you have an unknown acid, let's say, you're going to titrate it with a known concentration of base. If you have an unknown concentration of base, you'll titrate it with a known concentration of acid, and you can determine the concentration. And so first off, we're going to start off with this here. This is some sort of acid or base. And before we get started, we want to practice lab safety by putting our goggles on. All right. Now, like I said, I'm going to go ahead and just tell you that this is an acid, all right? And I'm going to tell you that it's an acid just because I know that what I put in there. But let's say that we didn't know. Well, we have things called indicators that tell us if something is acidic or basic. And the thing is there's many, many different types of indicators, and the indicators that we use depends on what we're trying to do. And so what I'm going to do is I'm going to use this particular indicator. This is not necessarily the best indicator to determine if something is acidic or basic, but this is what I'm going to use for the titration. And so this particular indicator, it is clear. If you put it inside of an acid, it remains clear. But if you put it inside of a base, if you put the indicator in a base, it turns pink. And so in an acidic solution, it's clear. In a basic solution, it's pink. Now it's not exactly that, but it's about that. So here we go. This is the acid and, well, the unknown here. And so what I'm going to do is I'm going to put this indicator in there. And when I put the indicator in there, notice how you only need to put a couple drops in there. Notice how it remains clear, which tells us that this is probably an acidic solution. And so because this is an acidic solution, what we're going to do is we're going to determine what the concentration of this is. Well, first off, there's 50 milliliters inside of this beaker. And because I know it's an acid, I'm going to titrate it with a known concentration of base. Now this happens to be a 0.1 molar solution of sodium hydroxide. So I know it's a 0.1 molar solution. There's 10 milliliters in here. And so what I'm going to do is, again, this is a very, very bad example of, this is not, there's no precision in what I'm about to do at all. I'm just using this as an example. But when I put this in here, let's say that I put a little bit of base in here. If we remember, first off, notice how it turns pink right there because the phenolphthalein is pink inside of a basic solution. But notice that the pink starts to go away as I'm stirring it, because what's happening is the base inside of here is reacting with the acid and it's neutralizing the acid. And notice how it turns back to clear. The reason why it turns back to clear is, yes, we did put a base in here. However, all of the base reacted with the acid, and there's still some acid left inside of here. And so this is actually an important concept. Because it's still clear, that means that there's still acid in here. And so the whole idea with a titration is that you continue to add a little bit of base at a time. So I added a couple drops, I swirl it around, and notice how the pink goes away. And what you do is you continue to add the base until the pink does not go away, until it turns pink and stays pink. Because again, if it is not pink, so notice how the pink goes away, that means there's still acid in there. So that means that we need to add more base until there's no more acid. And so you just keep adding some base. Eventually what will end up happening is it will turn pink and stay pink. Now, like I said, this is not, there's no precision in what I'm doing right now. I'm just showing you an example of what a titration is. And so notice how it's now pink and it's staying pink, meaning that the solution is now basic. Before it was clear, meaning that there was still some acid in there, but now we've reached the point at which it's pink and it's staying pink, which means that it's basic. Now this started off at 10 milliliters and it took about, and now it says it's about 6.5 milliliters. Because we started off at 10 milliliters and now there's 6.5 milliliters, we subtracted and we get about, it took about 3.5 milliliters of this for that to turn pink and stay pink. Now, when we do a titration, we do not use graduated cylinders. Instead, what we use is something called a burette. A burette is a very accurate and precise piece of glassware, and so it's very precise. You can actually, most burettes will go all the way to 2 decimal places. This will only go to 1 decimal place because of the lines on there. Sorry, that actually goes to 2. So, but the burette is actually very precise. Now, the other thing with a burette is you can control how much acid or base you put inside of the solution. And so this is, like I said, a very rough example of a titration. We're going to actually look at a titration for our lab later, but let's go ahead and get started on the notes. All right. So in an acid-base titration, a basic or acidic solution of known concentration, which we call the titrant, reacts with an acidic or basic solution of an unknown concentration, which we call the analyte, because that's the thing we're analyzing. Now, the known solution is slowly added, kind of like what I did with the sodium hydroxide, to the unknown one, while the pH is monitored. Now, in this situation, I didn't monitor the pH, but we're going to talk about what it'll look like as you monitor the pH. Now, at the equivalence point, which is the point in which the titration, or the point in the titration when the number of moles of base is stoichiometrically equal to the number of moles of acid, that's when the titration is completed. Now, what that's saying is when you've added enough moles of your titrant to react completely with your analyte. Now, an indicator is a substance whose color depends on the pH, so I used phenolphthalein in this situation. This particular one is clear inside of an acidic solution. It's pink inside of a basic solution. The reality is that this actually will turn pink around a pH of 8 or so. Now, the point where the indicator changes color is called the endpoint. Now, the endpoint is not the same thing as the equivalence point. The endpoint is where the color changes. Now, like I said, the color changes at a pH of around 8 or so for this one. I don't know the exact pH, but think about when you're neutralizing a strong acid and a strong base, you completely neutralize it at a pH of 7. And so the endpoint is going to be a little bit off of the equivalence point. Now there are, like I said, there's many pH indicators, and what we do is we select the right indicator that's going to give us an endpoint that's closest to the equivalent points. All right, so there are some indicators that will give us endpoints, closer to 7, let's say. They'll give us an endpoint closer to 8 or an endpoint closer to 6 or whatever. And there's different reasons why you would want that endpoint, and we'll talk about that in a moment. So again, the endpoint is when the color changes. That's where you end the titration. The equivalence point is the actual point in which all of the acid or bases reacted. Now, if we were to monitor pH, this is the graph that we would get. Think about this solution right here. As we were adding base to it, well, before we started adding base, what was the pH of it? Well, it was an acidic solution. So notice how if we were to be graphing this, it would start off somewhere in the a pH that is acidic. As we add base to it, that base is reacting with the acid. but we're only adding a little bit of base at a time. So what ends up happening is it's only reacting with a little bit of acid, and if we have acid left over, the solution will still be acidic. So notice how the first part of the graph is it starts off acidic and it's slowly getting less and less acidic. Now, the reason why it's slowly getting less and less acidic is because we're adding base and there's still acid in there. Now, the point at which we add the perfect amount of base to where the base reacts with all of the acid, at that point we have no more acid left and we have no more base. There's no base and there's no acid because all of it has neutralized each other. It's all reacted with each other. And that point is the equivalence point, which is on this graph. If we were doing a strong acid and a strong base titration, the equivalence point would be a pH of 7 because that's neutral. Now, the thing is that with a titration, a lot of times as you go past the equivalence point, you continue to add base afterwards. If there's no more acid, but we're still adding the base, kind of like what we did here, I actually added more than I should have here. What ends up happening is the solution then becomes basic. And so everything after the equivalence point represents the extra base that you've added to the solution. Now this is a unknown acid being titrated with a known base. This is a unknown base being titrated with a known acid. Notice how the curve looks exactly the same except for it's flipped. We're starting with a basic solution and it's an unknown base, and we add little bit of acid as we go, and as we add a little bit of acid it becomes less and less basic until we've added the perfect amount of acid. All of the base is neutralized, all of the acid is been neutralized by the base as well, and we get the equivalence point at 7 there. Now, something I want to point out in this graph is notice the x-axis. The x-axis represents milliliters. Notice how in this graph it shows that it took 25 milliliters to get to the equivalence point. That's going to be very important because that's the volume we're going to use to help us determine the moles of known titrant that we put in the analyte to then calculate the moles of the analyte. So again, we want to look at that. If we look at the one before that, it took, again, 25 milliliters, just a coincidence, the same, to get to the equivalence point. All right, so titrations involving a strong acid and a strong base will have an equivalence point that's equal to 7, all right? So have an equivalence point equal to 7. And we have not talked about acidic salts, basic salts, or neutral salts, but the reason why that it's a pH of 7 is because it produces a neutral salt. We don't really need to know about neutral salts. And so again, strong acid, strong base, pH 7. Now, look at this is a weak acid and a strong base. Notice how a weak acid, the equivalence point is above 7. Notice how it's actually a little bit above 8, which is what makes phenolphthalein great, because a weak acid equivalence point is going to be somewhere right above 8, and that happens to be the point at which phenolphthalein changes from clear to pink. Now, so notice it shifted up a little bit. Also notice how if you have a weak base and you're titrating with a strong acid, notice how the equivalence point shifts down. So now the equivalence point goes from 7 to a little bit below 6. So a titration involving a weak acid and a strong base will have equivalence point less than 7. So if you have an unknown weak acid, it'll have a pH greater than 7. The equivalence point will be greater than 7. Now, if you're titrating with a weak base, the equivalence point is going to be less than 7. And so where exactly it is, you don't need to know for this class. So again, here's an example of that. And that's it. So that's titrations. And so really it's very, very similar to solution stoichiometry. And we'll look at some examples of how we can calculate the unknown concentration, how we can look at a graph, a titration curve, and get the concentration of unknown from that. And then we're also going to talk about how we can actually produce that curve. So go ahead and watch the guided practice problems and do your independent practice, and we will go over more of this in class.